External forced convection as a heat transfer mechanism when a fluid flows over a solid surface. The main focus is the interaction between fluid flow, friction forces, and heat transfer at the outer surface. This phenomenon is very important in many engineering applications, such as aircraft, buildings, and wind turbines. The analysis of external forced convection is always linked to boundary layer and drag concepts. This introduction becomes the foundation for the entire chapter.
Lesson Plan: Heat Transfer. This slide shows the position of external forced convection within the overall structure of the heat transfer course. Previous chapters discuss conduction and the fundamentals of convection, which are prerequisites for this topic. External forced convection is placed before internal forced convection and natural convection. This order shows the learning path from basic concepts to more complex applications. Understanding this map helps students see the connection between chapters.
Learning outcome. This slide explains the learning outcomes that should be achieved after studying this chapter. Students are expected to distinguish between internal and external flows and understand drag and heat transfer coefficients. In addition, students should be able to analyze flow over flat plates, cylinders, and spheres. Tube bank analysis is also an important practical application. All these outcomes emphasize analytical understanding rather than memorizing formulas. External forced convection. This slide emphasizes the real-world relevance of external forced convection through examples such as aircraft, wind turbines, and buildings. Fluid flow over a surface produces friction and pressure forces that affect system performance. At the same time, heat transfer occurs between the surface and the fluid. Engineering design optimization strongly depends on understanding these two effects together. Therefore, external forced convection is always analyzed together with drag and heat transfer. Measuring drag force in a wind tunnel. This slide explains how drag force is measured using a wind tunnel. A vehicle or model is placed in a controlled airflow to simulate real conditions. The force acting on the object is measured using a force gauge connected to the model. This experimental data is very important for improving aerodynamic design and energy efficiency. This experimental approach complements theoretical analysis. Drag forces on flat plates. This slide distinguishes two flow conditions over a flat plate, namely parallel flow and normal flow. In parallel flow, drag is mainly caused by wall shear due to the boundary layer. In normal flow, drag is more influenced by the pressure difference between the front and back of the plate. These two mechanisms show that the source of drag can be different depending on the object orientation. This understanding is important in designing structures exposed to fluid flow. Check your understanding, number 1. This part serves to reinforce the concept that in parallel flow, drag is determined by wall shear. This concept is directly related to the formation of the boundary layer along the plate surface. If this idea is not well understood, drag analysis in many applications will be incorrect. Therefore, the main idea to remember is the dominant role of wall shear in this condition. This becomes the basis for the next discussion on friction coefficients. Drag in parallel flow. This slide explains that in parallel flow over a flat plate, there is no significant pressure drag. The entire drag force comes from friction between the fluid and the surface. Therefore, the drag coefficient is equal to the friction coefficient. This simplification is very helpful in engineering analysis because only one mechanism needs to be considered. This concept is often used in analyzing flow over long flat plates. Flow separation and wake region. This slide introduces the phenomenon of flow separation when the fluid can no longer follow the surface contour. As a result, a wake region with low pressure and turbulent flow is formed behind the object. This wake region contributes significantly to pressure drag. The larger the wake, the larger the drag force. Therefore, many aerodynamic designs focus on reducing the wake size.
Boundary layer over a flat plate. This slide shows the development of the boundary layer from a laminar region to a turbulent region along the plate. Near the leading edge, the flow is still orderly and the friction is relatively small. After passing the critical point, the flow becomes turbulent and both friction and heat transfer increase. This change of regime strongly affects both drag and heat transfer. Therefore, the transition location plays an important role in engineering analysis. Average friction coefficient in laminar flow over a flat plate. The value is obtained by integrating the local friction coefficient along the plate length. The final result shows that the average friction coefficient strongly depends on the Reynolds number based on the plate length. This relationship indicates that both flow properties and geometry control the magnitude of friction. This concept becomes the basis for calculating drag force in laminar flow. Check your understanding. Number 2. This part reinforces that the average friction coefficient in laminar flow does not depend on a single parameter only. The main controlling factor is the Reynolds number, which represents a combination of fluid properties, flow velocity, and characteristic length. By understanding this, it becomes clear that changing velocity or system size will directly affect friction. This concept is very important in aerodynamic and hydrodynamic design. It also helps in scaling experimental models. Effect of surface roughness on turbulent flow. This slide discusses the effect of surface roughness on turbulent flow. Surface roughness increases flow disturbances near the wall, which leads to a higher friction coefficient. For the same Reynolds number, a rougher surface produces higher drag. This shows that surface quality plays an important role in aerodynamic performance. Therefore, controlling surface roughness is a key aspect in engineering design. Variation of coefficients in boundary layers. This slide shows how the friction and heat transfer coefficients vary along the plate. In the laminar region, their values tend to decrease as the distance from the leading edge increases. When the flow enters the transition region, a sharp increase occurs due to rising turbulence intensity. In the turbulent region, the coefficients become higher and fluctuate. This pattern explains why the transition location is very important in engineering analysis. Heat transfer coefficient in mixed flow conditions, where part of the plate experiences laminar flow and the rest experiences turbulent flow. In the laminar portion, the heat transfer coefficient decreases gradually along the plate. After passing the critical point, the flow becomes turbulent and the coefficient increases sharply due to stronger fluid mixing. The average value represents the combined contribution of both regions. This concept is important for calculating total heat transfer over long plates. Jean-Claude Eugene Peclet. This slide introduces Jean-Claude Eugene Peclet and his contributions to heat transfer and fluid mechanics. His name is immortalized in the Peclet number, a dimensionless number that compares advection and heat diffusion effects. This number is very important in convection analysis because it indicates the dominant heat transfer mechanism. His works are known to be systematic and based on careful experiments. This recognition shows the importance of history in the development of engineering science. Flow over a flat plate with unheated start. This slide explains the condition when flow passes over an initial unheated section of a flat plate. In this region, the velocity boundary layer has already developed, but the thermal boundary layer has not yet formed. The thermal layer starts to develop only after the heated section begins. This affects the distribution of heat transfer along the surface. This concept is important in designing heating systems with limited heating zones. Check your understanding 3. This part emphasizes again that the thermal boundary layer does not start forming from the very beginning of the plate.
It only begins to develop when the fluid contacts the heated portion of the surface. If the initial part of the plate is not heated, there is no temperature gradient to drive heat transfer. This concept helps distinguish between velocity and thermal boundary layer development. This understanding is important for analyzing heat flux distribution.
Flow visualization over a circular cylinder. This slide shows a flow visualization around a circular cylinder that illustrates the formation of a wake behind the object. The flow pattern demonstrates instability and vortex formation due to flow separation. This wake region becomes the main source of pressure drag on the cylinder. Such visualization is very helpful for understanding phenomena that are difficult to grasp using equations alone. This approach is widely used in experimental aerodynamics. Flow over a circular cylinder. This slide explains the flow characteristics around a circular cylinder at a Reynolds number of about 2000. Under this condition, the laminar boundary layer separates from the surface and forms a turbulent wake behind the cylinder. This wake contributes significantly to the total drag force acting on the object. The flow pattern also shows significant energy dissipation. This analysis is highly relevant for designing cylindrical structures in fluid environments.
Transition to turbulence at Rex equals 5 times 10 to the power of 5. This slide shows that the transition from laminar to turbulent flow over a flat plate usually occurs at a critical Reynolds number of about 5 times 10 to the power of 5. This value is not absolute and is strongly influenced by disturbances and surface roughness. After this point, the nature of the flow changes drastically and friction increases significantly. This change also has a major impact on the heat transfer rate. Therefore, determining the transition location is very important in engineering analysis.
Drag coefficient for cylinders and spheres. This slide explains how the drag coefficient for cylinders and spheres changes with Reynolds number. In general, the drag coefficient decreases as the Reynolds number increases. In the critical Reynolds range, a sharp drop occurs due to changes in the boundary layer behavior. After transition to turbulent flow, separation is delayed and drag is reduced. Understanding this behavior is very important for shape optimization. Check your understanding number 4. This part reinforces that the sharp drop in drag coefficient at the critical Reynolds number is caused by the transition of the boundary layer from laminar to turbulent. This transition allows the flow to stay attached to the surface longer before separating. As a result, the wake size becomes smaller and pressure drag is reduced. This concept is often referred to as the drag crisis in aerodynamics. This understanding is important to explain why some objects experience a significant drag reduction at certain speeds.
Flow visualization over a sphere. This slide compares the flow around a smooth sphere and a sphere with a tripwire. On a smooth sphere, boundary layer separation occurs earlier, creating a wide wake. With a tripwire, the flow is forced to become turbulent earlier, delaying separation. As a result, the wake size becomes smaller and drag is reduced. This example shows how simple surface modifications can control flow behavior. Surface roughness effect on drag coefficient. This slide shows the relationship between relative surface roughness and the drag coefficient as a function of Reynolds number. Surface roughness can shift the critical Reynolds number and change the shape of the drag curve. Under certain conditions, roughness can actually reduce drag by triggering an earlier transition. However, at very high Reynolds numbers, roughness usually increases drag. This shows that the effect of roughness strongly depends on the operating condition.
Surface roughness and drag coefficient. This slide summarizes the effect of surface roughness on drag behavior, including the example of a golf ball. Properly designed roughness can reduce drag by delaying flow separation. This works by accelerating the transition to turbulent flow near the surface. However, if the roughness is too large, drag can actually increase.
Therefore, surface roughness must be carefully controlled in engineering design.
Surface roughness effect on drag. This slide emphasizes that the effect of surface roughness on drag depends on the Reynolds number. At lower Reynolds numbers, roughness can help reduce drag. In contrast, at high Reynolds numbers, smooth surfaces usually give lower drag. This shows that there is no single universal solution for all flow conditions. Surface design must always consider the operating Reynolds number range.
Local heat transfer on a cylinder. This slide explains that the local heat transfer coefficient on a cylinder is not uniform along its circumference. The maximum value usually occurs near the stagnation point at the front of the cylinder. After that, the coefficient decreases as the angle increases due to boundary layer development and flow separation. Increasing the Reynolds number raises the overall heat transfer level. This pattern is important for designing cooling of cylindrical components.
Check your understanding. Number 5. This part reinforces that the maximum heat transfer on a cylinder occurs near the stagnation point. At this point, the fluid first contacts the surface, and the temperature gradient is the highest. As the fluid flows along the surface, the boundary layer thickens and heat transfer decreases. This concept is consistent with the previously discussed distribution of the heat transfer coefficient. This understanding is important for placing cooling or heating systems.
Empirical Nusselt correlations for cylinders. This slide introduces empirical correlations to predict the Nusselt number for various cylinder shapes. Each cross-sectional shape and Reynolds number range has its own correlation. These correlations are very useful in practice because they allow quick calculations without complex simulations. However, their use must always respect the validity range of the Reynolds number. In this way, heat transfer for various geometries can be estimated reliably.
Flow patterns in tube banks. This slide compares the flow patterns in inline and staggered tube bank arrangements. In the inline arrangement, the flow tends to be more streamlined, with more periodic vortex shedding and lower turbulence. In the staggered arrangement, the flow becomes more chaotic and fluid mixing increases. This increase in turbulence usually enhances the heat transfer rate. However, this benefit comes with an increase in pressure drop.
Tube bank arrangements. This slide explains the geometric differences between inline and staggered tube bank arrangements. In the inline arrangement, the spacing between tubes is uniform, allowing the flow to pass more easily through the gaps. In the staggered arrangement, the tubes are offset, forcing the flow to change direction and mix more strongly. This difference in arrangement also affects the effective flow area. Therefore, the geometric configuration strongly determines flow and heat transfer characteristics.
Check your understanding. Number 6. This part emphasizes again that the main characteristic of a staggered arrangement is higher turbulence and higher heat transfer. This happens because the flow cannot pass straight through the tubes and must continuously change direction. As a result, fluid mixing increases and the boundary layer is disturbed more frequently. The consequence is a higher pressure drop compared to the inline arrangement. This shows the trade-off between heat transfer and pressure loss.
Nusselt number correlations for crossflow over tube banks. These correlations are valid for a wide range of Reynolds and Prandtl numbers. For staggered arrangements, heat transfer is usually higher than for inline arrangements due to stronger turbulence. The effect of tube spacing is also included in the correlations to improve accuracy. With these correlations, designers can practically estimate thermal performance.
Correction factor for Nusselt number. This slide explains the correction factor used when the number of tube rows is relatively small. For tube banks with fewer than about 16 rows, the effect of the number of rows is still significant on heat transfer. This correction factor increases as the number of rows increases and approaches 1 for a large number of rows. Inline arrangements usually require a larger correction compared to staggered ones. This concept is important to avoid overly optimistic calculations. Friction and correction factors for tube banks. This slide discusses the behavior of the friction factor in tube banks. For inline arrangements, the friction factor decreases as the Reynolds number and row spacing increase. For staggered arrangements, the friction factor is generally higher due to stronger turbulence and mixing. A correction factor is used to account for the effect of transverse and longitudinal tube spacing. All of this shows that pressure loss is very sensitive to tube bank geometry. Check your understanding. Number 7. This part reinforces that the staggered arrangement produces a higher friction factor than the inline arrangement. This is caused by the higher level of turbulence and flow mixing. The stronger the flow disturbance, the larger the pressure loss. This concept is consistent with the previous discussion about the trade-off between enhanced heat transfer and increased pressure drop. This understanding is important in industrial heat exchanger design.
References. This slide lists the main source of the figures and materials, namely the book Heat and Mass Transfer by Chengel and Gajar. This reference shows that the entire discussion is based on internationally recognized standard literature. This book is widely used as a primary reference in heat transfer courses. By knowing this source, students can further deepen the material independently. A strong reference also increases the reliability of the material being studied.